Earth, a 4.5 billion-year-old planet, still evolving. As continents shift and clash, volcanoes erupt, and glaciers grow and recede, the Earth's crust is carved in numerous and fascinating ways, leaving a trail of geological mysteries behind. In this episode, Iceland, the world's largest volcanic island, is explored. This barren and alien landscape generates 1/3 of the world's lava. Steam billows from the ground, and boiling water is thrust into the air. It's a land of violent extremes where fire meets its nemesis, ice. And where clues to understanding Iceland's formation also provide a window into the formation of the Earth itself. In the middle of the North Atlantic Ocean lies Iceland, a lone island only 300 miles wide. A volcanic hotbed, it holds some of the most diverse geological wonders known to mankind. To understand how it formed and the dynamic forces that are shaping this land, scientists are scouring the strange landscape for clues. And the investigation starts here in the southwest of Iceland, the Thingvellir Plain. This broad inland valley runs through the center of Iceland. Giant cracks scar the valley floor, leaving this unusual landscape behind. Geologist Mike Poland believes they're a major clue in the mystery of Iceland's formation.
I'm standing in a really spectacular place. There's evidence for volcanic activity all around. This valley is covered in lava, and the plain is being ripped apart. Everywhere I look, there's massive tears in the ground, like this one right here. This crack is getting bigger and bigger every year. In fact, this entire valley is spreading apart at about the same rate that fingernails grow. Now imagine the forces that must be involved to rip the land apart like this.
Something powerful is spreading this valley at a rate of 1 inch a year. A force so immense, it's pulling the entire country apart. But what force on Earth could have such power? In 1912, German climatologist Alfred Wegener found an essential clue. Browsing through maps, he noticed that the great land masses of the Americas and Eurasia appeared to fit together. This observation led Wegener to propose a radical new theory, that these great continents had once been joined together. So some unseen force must have pushed them apart, allowing water to rush into the space between them, creating the Atlantic Ocean. It was inspired detective work and a major step forward in the search for what was pulling Iceland apart. But with no method to prove such a force existed, Wegener's theory was ignored for the next 40 years. Then, in 1946, new evidence was discovered to support Wegener's ideas. The U.S. Navy, using a technology called sonar imaging, mapped the Atlantic Ocean floor for the first time. The pictures revealed a 10,000-mile network of underwater mountains, separated by a giant tear which passes through the center of the Atlantic. Scientists call this the Mid-Atlantic Ridge. This huge tear through the Earth's crust is the boundary between the American and Eurasian plates. And the tear runs right through the center of Iceland.
I'm actually standing on what's essentially the ocean floor, where the Mid-Atlantic Ridge comes onto land. And it splits the North American plate on this side from the Eurasian plate at this side. And the Mid-Atlantic Ridge starts way south down by Antarctica, comes all the way up through the Atlantic, and splits this country right in two.
Scientists suspected this was pushing the continents and Iceland apart. They came up with a theory. Deep below the ocean, convection currents of molten rock tear open the Earth's crust, allowing magma to seep up and push the continents apart. But there was a problem. It was so deep, scientists had no way of proving whether magma was seeping through the crust at the center of the ridge. Until in 1974, Alvin, a human-operated submersible, was launched by the Woods Hole Oceanographic Institute. With its ability to withstand deep sea pressures, scientists could finally travel down to the depths needed to reach the mid-Atlantic ridge. It was by examining the tear that runs through the center of this ridge that they spotted the evidence they'd been looking for. Hot volcanic gases billowing into the ocean. Finding this told them that the mid-Atlantic ridge was highly volcanic and, like a giant wedge, was capable of spreading great land masses apart. Iceland's cracked Thingvellir Valley is a continuation of the mid-Atlantic ridge. The same process that's pushing America further away from Europe is happening here on land. Finally, here was a force powerful enough to explain why the cracks are getting wider and Iceland is getting bigger.
As the ridge continues to spread, it's going to add more and more land to Iceland. So in a way, Iceland will start getting longer and longer. In an east-west sense as the plates spread apart from one another. So in a way, Iceland is not getting torn apart so much as it's getting built.
The investigation into how Iceland is growing has revealed cracks on the Thingvellir Plain are widening at a rate of 1 inch a year. And hot gases prove that this spreading force is volcanic, forming the mid-Atlantic ridge, which cuts right through Iceland. Scientists concluded it's this that's widening the country. Convection currents of hot rock pull the mid-Atlantic ridge apart. Magma surges up to fill the cracks, and as it approaches the surface, it cools, hardens, and forms new land. Like a conveyor belt, it continually pushes Iceland apart. California's greatest cities and millions of her citizens live in constant peril. Since records began, there have been 13 large earthquakes along the San Andreas Fault.
The water lines have ruptured. There is no water coming out of the fire hydrant.
Which makes it crucial to investigate the most important question. When will the next big earthquake hit the San Andreas Fault? The earthquake struck on a Wednesday, just before dawn. The ground shook violently for 45 seconds, igniting fires that raged unchecked for the next 4 days. "28,000 buildings, a tenth of the entire city, were destroyed, and more than 3,000 people, 1 in every 100 of the population, were killed. With a magnitude of 7.8, it's in the top 20 of North America's strongest ever earthquakes. The scale of the Great San Francisco earthquake shocked the nation. But no one understood what had made the city shake. So, just 3 days after the earthquake, the state of California asked one of the world's most famous geologists, Andrew Lawson from California State University, to investigate what had destroyed the city. He and a team of 25 scientists began collecting damage evidence in the city and surrounding countryside. There were roads that had buckled, rail tracks that had twisted. The most startling evidence of all, that came near the town of Bolinas in Marin County, to the north of San Francisco. This picket fence had an 8-foot gap in the middle. Before the earthquake, it was a solid boundary fence dividing two fields. But when he recreated what had happened, Lawson realized that the land had jolted apart and torn the fence in two. Plotting the evidence on a map around San Francisco revealed a surprising pattern. Because connecting the dots drew a straight line. And at every point, the Earth moved in the same way, on the coast to the north, inland to the south. This line of weakness was the culprit they were searching for. South of San Francisco, the suspect line ran underneath a lake, the Laguna de San Andreas. So now, the earthquake perpetrator at last had a name. Professor Lawson, who a decade earlier had identified cracks in the earth here as a harmless rift, now rechristened it the San Andreas Fault. Running south across the seabed, the San Andreas finally runs out of ocean and hits the land. This broken line of rocks, stretching in from the sea, marks where the San Andreas hits land 12 miles south of San Francisco.
We're here at Muscle Rock, and we're essentially standing on the San Andreas Fault right now. And if there was an earthquake, I don't know what would happen right here, but I wouldn't want to be here.
This Pacific coastline, where cliffs crumble slowly into the sea, is the boundary between two of the Earth's massive continental plates. Separated by the San Andreas Fault, two vast separate blocks of the Earth's crust lie directly alongside each other. Here, the continent of North America lies slightly on top of the adjacent section of crust which holds the Pacific Ocean. The join can be seen where these lower, darker rocks are overlaid by light-colored sedimentary rocks.
These rock types differ by more than 100 million years in age. Two rock bodies that are not similar in any way have been brought together.
The fault line was exposed to geologists when the cliffs collapsed here in the 1906 earthquake. But back then, nobody understood how and why the two different types of rock were next to each other. Until around 40 years ago, when the answer was finally revealed by the theory of plate tectonics. The theory showed that the Earth's crust consists of separate moving plates on which the oceans and continents sit. Around 200 million years ago, the heavy Pacific Ocean plate collided with North America and started sinking underneath the lighter continent. Professor of Geophysics Mark Zoback studies that process, called subduction, in his laboratory at Stanford University.
For many millions of years, prior to the existence of the San Andreas Fault, the Pacific plate was subducting beneath North America. The oceanic plate was diving down, and that process went on for, well over 100 million years. So a tremendous amount of activity was occurring.
As the unstoppable force of one plate met the immovable object of the other, they were forced to change direction.
About 20 million years ago, the plate motions were such that the Pacific plate had to start sliding north with respect to North America. And now, the principal motion is this sliding process between the two plates. And 20 million years ago, the San Andreas Fault was born.
It was the moving plates that crushed different types of rock together, just as here at Muscle Rock. At last, the investigation knows what it is dealing with. The San Andreas Fault is 800 miles long, emerging from the seabed north of Point Arena in Northern California and running down to the Salton Sea in the south. The evidence is coming together. Clues from the 1906 earthquake, such as the picket fence that was torn apart, prove that the land was moving. connecting the dots identifies the straight line of the San Andreas Fault. And Mussel Rock uncovers different plates of the Earth's crust on either side of the fault line. The investigation moves to an even more remote desert spot, the Carrizo Plain, 160 miles north of Los Angeles. Here lies a dried-up riverbed, which takes an unusual course. Coming down off the hills, the creek bed takes a sudden, sharp turn to its right. A few hundred feet later, it makes an equally odd 90-degree turn to the left. The creek crossed the line of the San Andreas Fault, but early geologists were mystified. Why did it bend in this way? The scientific pioneers were limited to studies on the ground. Nowadays, Hudnut has an advantage. He can take to the air.
The San Andreas Fault, where it cuts through the Carrizo Plain, it almost looks like a scar, and it was caused by repeated earthquakes in the past.
Along the long line of hills marking the course of the San Andreas, Hudnut spots the puzzling bends that he's seeking.
Oh, if we could swoop along the fault through here, that would be awesome. Oh, there's a great angle. See that right angle offset channel with the elbow in it right there? That's a classic one right there.
Hudnut's aerial view of the creek bed shows that the river once flowed straight on across the fault. But little by little, a series of earthquakes along the San Andreas dragged the creek away from its original course. Recreating how the land had moved showed Hudnut that the two parts of the creek had traveled more than 300 feet apart.
So if you imagine the North American plate is fixed and the Pacific plate is moving to the northwest, the Wallace Creek site records that offset because the channel was straight across the fault, but it's been offset through time.
Earlier investigators had already radiocarbon dated the land on each side of the fault here, revealing that it took 3,000 years to change the creek's position. So, knowing the distance and the time it took to do it, lets Hudnut calculate the average speed with which the two land masses are moving past each other. 300 feet in 3,000 years. 1 foot per decade. Just over an inch a year. But this was never a steady, sliding 1 inch a year movement. The reality was a series of sudden, small jumps whenever tension built up enough between the two moving plates to overcome friction between the rocks and rip the land apart with an earthquake. It's an important moment for the investigation. Knowing how fast the land is moving not only reveals the stress that's building up, but also the risk of an earthquake. The village of Parkfield has a population of just 37 people and a bridge which spans right across the San Andreas Fault. The bridge separates the Pacific Plate on one side from the North American Plate on the other. And the bridge railings have started to bend.
I'm right now on the Pacific Plate on the west side of the San Andreas Fault. And you know, the San Andreas comes off the flank of that hill and right across that field, right under the bridge, and then right over by the corner of that building or that fence post, and then on off to Middle Mountain.
Look 20 million years ahead. If the plate movements continue to follow their pattern, Los Angeles will end up becoming a suburb of San Francisco. Deep, dark, and full of mystery. This is Loch Ness in the Highlands of Scotland. For 1,000 years, there have been claims that this vast lake hides a strange and terrible secret. the fabled Loch Ness Monster. A mythical beast, suggested by some as a descendant of the dinosaurs which once roamed this part of Scotland. Loch Ness would be the perfect hiding place for a prehistoric monster. At 23 miles long and a mile wide, this vast freshwater lake covers the same area as New York's Manhattan Island, and it's more than 700 feet deep. But the monster is not the only mystery that surrounds Loch Ness. In the hills above the loch, there is a type of rock whose origin baffled scientists for years. It's a sandstone, and it's the start of the investigation into how Loch Ness was made.
It's known as the Old Red Sandstone, and it's given that name because it's red and it's a sandstone. And it's called old because it's about 350 million years old.
The Old Red Sandstone runs down one side of Loch Ness. But the most astonishing fact about these rocks is not their age, but where they come from.
These rocks actually belong to my homeland of North America because these rocks originated on the North American continent and then have separated from North America. But in many ways, this is almost a little bit of home for me here in Scotland.
But how do geologists know that this Old Red Sandstone comes from 3,000 miles away, on the other side of the Atlantic Ocean?
These rocks are identical in age and character to the rocks that actually form the Catskill Mountains. And so this part of Scotland belonged to northeastern North America.
For more than 1,000 years, Old Red Sandstone has been used for building castles in this part of Scotland. But it's also been quarried in the US and used for brownstone buildings in New York City. Under the microscope, rocks from both continents have an identical crystal structure, and chemical analysis has also proved that they're exactly the same age. But how did part of America end up on the shores of Loch Ness? Geologists now know that the only force powerful enough to produce this extraordinary mix of rocks is plate tectonics. Plate tectonics is the process by which the giant plates of the Earth's crust are driven slowly across the planet's surface by vast convection currents deep in the Earth's hot mantle. In the Loch Ness region, the evidence in the road cut reveals that incredible pressures forced the crust deep down into the Earth, where it was melted, deformed, mixed together, then finally brought back to the surface. After that, for another billion years, this ancient landmass quietly eroded down to a rough, rolling landscape. The investigation into how Loch Ness was made will next uncover the geological structures which would eventually create Loch Ness. The search for evidence begins with a 19th century scientific mystery. In the 1880s, geologists in Scotland were baffled by a sequence of rocks they found north of Loch Ness. Here in a remote hillside lay the problem. A huge mass of very old Lewisian gneiss was lying on top of much younger rocks. But the 19th century geologists had never encountered this before. In their experience, younger rocks always lay on top of older beds. Then, one scientist invented a novel approach to try to solve the puzzle.
A survey geologist back in the Victorian age, 125 years ago, mapped this area, and his name was Henry Cadell. He went back to Edinburgh and he worried about what he'd seen in the field and thought, how do I replicate what I've seen? How does this happen? So he built a model and he attempted then to show, using the model, what it was that he saw in the field.
Cadell's model was simple. He suspected that some force had squeezed the rocks horizontally to make this upside-down sequence, so he built an apparatus containing layers of sand and clay to test his ideas. Professor Underhill is using a replica of Cadell's equipment, filled with alternating layers of black sand and plaster of Paris, to try and duplicate Cadell's experiment. Turning the screw winds the block forward, imitating the horizontal pushing force that Cattle thought was the culprit. As the horizontal force increases, the layers are pushed over each other along a shallow plane, which geologists now call a thrust fault.
And we've got the first thrust appearing. Oh, look at that. Another thrust going in.
The experiment showed Cattle exactly how older layers, the ones on the bottom, are pushed over and on top of the younger layers along the plane of the thrust fault.
There's some beautiful structures in here. There's a thrust fault running through here, which duplicates the white layer. And another one through here, and the final thrust fault, which is at the lowest angle, out here towards the left-hand side. A success in terms of a simple model replicating what we see on the ground. And I can see how Cattle and others, when attempting such things, began to understand what it was that they saw in the field. They could replicate it in a simple, crude model, but replicate it in a very successful manner.
Once Cattle and his colleagues understood the principle of thrust faults, the apparently illogical sequence of the rocks they saw in northwest Scotland began to make sense.
Well, the slope represents a thrust fault. What we have underneath it is a bedded, younger quartzite succession, which is pink. Above it, the grey rock, the rubbly grey hillside we see above, is the Lewisian gneiss again. And the surface in between, which is putting older rock, the grey material, onto the pink rock, the younger material, is the thrust fault, just like in the model that we saw before.
Geologists now know that a thrust fault is the smoking gun that shows where continents have collided. But which continents were colliding to make the thrust faults in Scotland? And how were they involved in making Loch Ness? The scientists' trail now led them to another thrust fault, the Moyne Thrust. The Moyne Thrust is one of the biggest thrust faults on Earth. Running for 120 miles down the northwest of Scotland, it's mostly hidden from view. But Professor Underhill has found one of the rare locations where the thrust can be seen on the surface. This apparently insignificant join between two rock layers is the actual line of the thrust. And it reveals a geological bombshell. The dark layer above the thrust comes from England, but the surprise lies in the yellow limestone below it. Just like the old red sandstone at Loch Ness, this rock comes from North America. This one small piece of evidence has enormous implications for the formation of Loch Ness.
The amazing thing about this contact is that it's the meeting point between two continents. So here we are on a wet Scottish hillside on a Sunday afternoon, and I am touching the contact between effectively America and northwestern Scotland on one hand and England on the other, as was 425 million years ago.
But how did these two ancient continents collide? 450 million years ago, a supercontinent containing North America and Scotland lay deep in the southern hemisphere. At its margin was an ocean wider than the present-day Atlantic. On the other side was England and Europe. But the forces of plate tectonics were slowly pushing the two land masses together.
Well, around 450 million years ago, there was a major ocean where we're standing now. It was called the Iapetus Ocean, and it separated America and northwestern Scotland on one hand from effectively southeastern Scotland and England on the other hand. Now, what happened in the 20 million years after that, that ocean closed and eventually was closed sufficiently that two continents collided into each other.
The collision between America and Europe pushed massive layers of rock over each other, forcing upwards a range of mountains higher than the Himalayas are today. Still firmly attached to America, Scotland and England became fused together. But what did this collision have to do with the making of Loch Ness? The loch itself provides the most fundamental evidence.
The one thing that's quite striking about Loch Ness is that when you look at it, particularly from this perspective, you can see that it runs straight, almost straight as an arrow. And that straightness goes on for about 20 miles. And as a geologist, that tells me that there has to be a control on this topographic straightness because nature doesn't produce things in straight lines. And so there is a structure here that is controlling the overall shape of Loch Ness itself.
This structure is the Great Glen Fault, a major geological fault line formed during the continental collision 425 million years ago. It runs for more than 300 miles right across Scotland, slicing the country in two. Loch Ness exactly follows the line of the Great Glen Fault.
The Great Glen Fault, it's not a thrust fault like the Moyne thrust where material has been pushed up over. It's not a normal fault where material drops down vertically. It's lateral motion. The Great Glen Fault is Scotland's version of the San Andreas Fault. It's just 400 million years older.
The Great Glen Fault is no longer active, but this giant split in the Earth's crust has been a feature of the Scottish landscape for more than 400 million years. It's the foundation of Loch Ness, and without it, the loch could not exist, nor could the legend of the Loch Ness Monster. The investigation into how Loch Ness was made has uncovered more evidence. The discovery of thrust faults showed geologists what happens when continents collide. Yellow limestone from North America found at the Moyne thrust proves that America and Scotland crashed into England 450 million years ago. And the shape of Loch Ness reveals the straight line of the underlying Great Glen Fault, formed during that continental collision. Geologists know that this kind of magma comes from deep within the Earth. It usually erupts on the surface when tectonic forces split the Earth's crust apart. Is that what happened here 60 million years ago?
At that time, Scotland was still joined to North America, but the two continents were being stretched and thinned due to tectonic forces. And that allowed molten rock, or magma, from deep within the Earth to well up and to be erupted from those volcanoes. And eventually, that volcanic activity led to the development of a new ocean between Scotland and North America, the Atlantic Ocean.
So the lavas are the trail of evidence which show that the opening up of the Atlantic Ocean began with volcanic eruptions all over Scotland. As magma erupted under the ocean, the seafloor spread out, slowly pushing Scotland and America apart. Earth is a blue planet, engulfed by water. But in this desolate chunk of northern Chile, you won't find a single drop. Wedged between the Pacific Ocean and coastal volcanoes to the west, and the Andes to the east, is Atacama, the driest desert in the world. "600 miles long and narrow, on average just 100 miles wide. It's the same size as Iowa. Now, scientists are on a mission to find out how it was made. "150 million years ago, the Atacama Desert was a seabed, covered by ocean waters. But today, some areas in the desert are 2 miles above sea level. In the journey to find out how this happened, scientists take the investigation to the eastern edge of the desert. This strange landscape is the largest geyser field in the southern hemisphere.
We're up at the El Tatio geyser field. You can see around us that there's plenty of hot springs and geysers. There's plenty of steam around, and this is because the air is cool and the water is hot, and so you have a lot of steam and bubbling springs.
The boiling water is being heated deep underground.
The geysers and the hot water that you find up at El Tatio are indications that you have a body of hot rock underneath us. And another indication is you have a bunch of volcanoes surrounding this basin.
The Earth here is violently alive. Molten rock erupts onto the surface, forming volcanoes. The fiery volcanoes and the boiling geysers are evidence of a turbulent process happening deep beneath the desert. Here, the Pacific Ocean crust is being forced underneath South America, much like a spatula going underneath a pizza. This geological process is called subduction.
You have the Pacific Plate colliding with the continental crust, and the Pacific Plate is actually heavier and it slides underneath the continental crust. And as it does so, it heats because it gets to a depth of about 60 miles and it becomes molten.
This crucial depth is called a melting zone. Hot molten rock then thrusts upward to form the active volcanoes that ring the El Tatio geyser field. This process gives scientists a hint to what lifted the desert out of the ocean. More clues are found on the opposite side of the desert. Geologists know that these coastal hills were also once volcanoes. Today, they're completely dead, but modern dating techniques show that they first erupted over 195 million years ago. It's a crucial piece of evidence which reveals when the Pacific Plate first began to force its way beneath South America. At that time, the desert, indeed all of Chile, was underwater. Over time, the melting zone was pushed further and further inland, first igniting the coastal volcanoes. As the melting zone passed beneath the desert, it formed new crust, thickening and raising the land. The Atacama Desert slowly emerged. $50 million years ago, this same process began to raise the Andes. Today, the melting zone is 140 miles inland, and the molten rock it produces ignites volcanoes and fuels El Tatio's geysers. The mystery of how a desert can rise from the sea can be solved. Geysers provide evidence that molten rock exists deep underground. The existence of active volcanoes shows the movement of one continental plate under another. Extinct volcanoes show this process began at the coast and pushed inland, raising the desert above the ocean.